Okay, today's lesson's on complex numbers. And what the complex number is it's really all numbers. And what we're used to seeing are the real numbers, but the complex numbers really have an imaginary portion and a real portion. So every number can really be written as A plus BI, where A is the real portion and BI is the imaginary portion. So what we're used to dealing with is if this B would be 0, the imaginary portion would become 0, and that just leaves us with a real number only. That brings us into the real numbers and all their subsets going down this way. If the real portion becomes 0, then that leaves us with just the imaginary portion, and then we come down to this side and we get an imaginary number only. But the thing to realize is really all the numbers are part of the big complex number system, which is A plus BI. Okay? We're just used to dealing with these where the imaginary portion isn't there. Okay? So let's talk about what an imaginary number is. Now, before I do that, here's a little thing. This is right out of your book. So what you can see is it's got a little bit of what I just said. We have the real numbers, okay, real numbers only. That means there's no imaginary portion. And the A plus 0i, the imaginary portion is 0, and I get the numbers I'm used to dealing with. For the ones that are pure imaginary, notice that it says 0 plus BI. The real portion is 0, leaving me with just a true imaginary number. You can see that these numbers don't have a real portion. They're just 4i and 6i, where the I designates that they're an imaginary number. Okay, so I want to go through a couple things here, what creates an imaginary number, and then we can have a stopping point here in a second. This is what creates an imaginary number, a negative square root. Now, on the numbers we're used to dealing with, if I would have 4 times 4, well, that's equal to 16. So the square root of 16 is equal to 4. Notice that the number under the square root is a real number. Consequently, if I have a negative 4 times a negative 4, negative times a negative, I get 16. So a square root of 16 could also be a negative 4. Notice that there is no negative under the square root. So in the numbers that we know, there is no way that I can get a negative underneath the square root sign. But it does exist in the complex number system. So what the definition of an imaginary number is, it's the square root of a negative 1. And the square root of a negative 1 is I. So if we ever see this square root of a negative 1, we can just get rid of the square root of a negative 1 and call it I. So here's an example of how you can simplify square roots with imaginary numbers. I have a negative 4 underneath the square root sign. Well, I can think of that as a negative 1 times 4. I'm just splitting the negative 4 up into negative 1 times 4. Well, what's going to happen is the negative 1 will be I, and the 4 comes out as a 2. So the answer, or how I would simplify it, would be 2I. So another way to think of it is anytime you have a negative under a square root, you can just bring that negative out as an I. And that's how we simplify these imaginary numbers when they're square roots. Okay, so let's go through a couple of these. What we need to do is just figure out if these are going to create real numbers or if they're going to create imaginary numbers. Well, it's the square root of 9. That'd be 3, right? It's a real number. Square root of 0 is 0. It's a real number. Here, there's a negative on the outside. That's not a problem. It's only when it's under the square root, so the 4 comes out as a 2. This would be a negative 2, because this would be a 2 coming out. This would be equal to the square root of 4 is 2. The square root of 9 is 3. The square root of 2 is just the square root of 2. That's not going to be simplified. But this one has a negative underneath the square root sign, so this is just going to be I. Right, in this part, now what we're going to do is we're going to actually simplify some square roots that will have some imaginary numbers. And remember, when you simplify a square root, what you have to do is you have to get all perfect squares and all imaginary parts out. So here's an example. What I have is I have the square root of a negative 48. Well, I know that the negative part of that is going to just simply come out as an I. Now, you could write it as a negative 1 if you want, or you could just simply say, okay, this negative is going to come out as an I like that. That's fine, too. But anyway, that's got to come out of the square root. Then for the 48, what you have to say to yourself is, are there any perfect squares in 48 that I can factor out? And sure, it's 16 times 3, and then what you would do is the 16 would come out as a 4, because the square root of 16 is 4. So what this would be now, I've pulled the 4 out, I've pulled an I out, so those would be 4I. The 3 is still left under the square root, so 4I times the square root of 3. That's how that would look. Now the next one is another example. I have a negative 3 times the square root of a negative 50. Now this negative 3 is going to stay on the outside of the square root. This negative portion is going to come out as an I. And then I have to ask myself, well, can 50 be simplified? And sure enough, it's 25 times 2, so the 5 will come out because the square root of 25 is 5, so the 5 comes out. And what's going to happen is this 5 will multiply by the negative 3, because the 5 has come out of the square root. 5 times the negative 3 is a negative 15, and the I is right there. So negative 15I times the square root of 2. Okay, and what you guys, this is just a note for the future, is in a day or two we're going to be solving problems with this. That means there's going to be an equal to sign, and you're going to be saying what value of x makes the situation true. When you do that, you're going to be taking a plus or minus square root. These are simplifications, so you don't take a plus or minus. You don't put like, oh, it's a plus or minus 3 times the square root of 2. This you have to do when you solve, not when you simplify. So we're not going to be doing any of that in this simplification portion, all right? So let's go ahead and take a look at a couple of these problems and see how they come out. So if I have the square root of a negative 4, so what's going to happen is the negative comes out as an I, and the square root of 4 is 2, so I get 2I. Okay, on this one here, this negative will come out as an I, and then the square root of 12. Well, I can think of this 12 as 4 times 3, so we know that this 12 is really 4 times 3, and the 4 can come out as a 2. So this is going to be 2I. The square root of 3, or the 3 is left underneath there, so I have 2I times the square root of 3. For this negative 36, this comes out as an I. The 36 comes out as a 6. The 6 will have to multiply by this negative 1, giving me a negative 6I. And the last one, I have a negative 54. Well, 54 is 9 times 6. So I have a perfect square under the square root. The 9 will come out as a 3. The 3 will multiply by the 2. And the negative comes out as an I. So I would have 6I, right? The 6 is 3 times 2. My I came from the negative, and I have a square root of 6, because the 6 still has to stay underneath the square root sign. Right, here's some more fun we can do with these imaginary numbers. Now look what's happening. I'm starting to put powers on the i's. So what's going to happen is we know that I is equal to the square root of a negative 1. So what happens when I square I? Well, think of it like this. You're square rooting, because I is the square root of a negative 1. And now since I'm squaring I, that means the square root of a negative 1 is squared. Square root squared. Well, that just pops the square root off, and it's equal to a negative 1. So this is a really important concept, is that I squared is equal to a negative 1. Anytime you see an I squared in a problem, you can replace it by a negative 1. And what's kind of interesting about that is notice that I have an imaginary number, but when I square the imaginary number, this is imaginary, so to speak, and this becomes a real number. So an imaginary number squared is a real number. So maybe that's going to help us in the future, sometimes getting rid of imaginary numbers. We'll see. Okay, let's look what happens when I take I cubed. Well, I can think of I cubed as I squared times I. Well, we know I squared is a negative 1, so that would be a negative 1 times I. So I cubed is the same thing as a negative I. Now, you don't have to memorize that. You can figure that out just because you know that I cubed is equal to I squared times I squared is a negative 1. I to the fourth. Okay, I to the fourth is equal to I squared times I squared. Well, I squared, we already proved up here, was a negative 1. Negative 1 times negative 1 is 1. So look what happens. I to the fourth is just simply equal to 1. Like I said, don't memorize them, just figure them out. And then it just repeats, because I could think of I to the fifth. Well, that's I to the fourth times I. I to the fourth is 1, so 1 times I is I. So they just repeat over again, but you can figure that out by the powers, okay? So let's take a look at an example. I have I times the square root of 2. Now, this power will distribute in. It will not distribute in if this was an addition sign, like if it was I plus the square root of 2. You can't distribute the power in. But when it's multiplied, it does. So this is going to be I squared times the square root of 2 squared. I squared is a negative 1. The square root of 2 squared is just 2, so that would be equal to a negative 2. For the next one, I have I times the square root of a negative 4. Well, this negative will come out as I. The 4 comes out as a 2 because the square root of 4 is 2. So what I'll have is I times 2. That's going to be equal to 2 times I squared, but I squared is just, that's the top of the I there. 2 times I squared is a negative 1. It's going to give me a negative 2. Okay, the next thing we're going to do is graph the complex numbers. This isn't in the book, but it's a good thing to know, and it's really easy. When we graph complex numbers, we use a different kind of graph. The x-axis is where we plot the real number portion. The y-axis is where we plot the imaginary portion. So this is just like plotting regular numbers, except that the real portion will go on the x, the imaginary on the y. So let's try plotting this one, 3 plus 4i. Well, here's my real portion. So I go over 3 divisions in the real portion, and then I go up 4 divisions in the imaginary because the imaginary portion is 4i, so over 3 to the right, 4 up, there's my point, right there. Okay, number 2, negative 6 in the real, negative 2 in the imaginary. So negative 6 in the real would go 1, 2, 3, 4, 5, 6 in the real, and then the imaginary is down 2, so the point number 2 would be down here. All right? Number 3, well, that's just got a real portion only 7. So the real portion is on the x-axis, 1, 2, 3, 4, 5, 6, 7. That point would be right here. Number 4 is 5i. So that only has an imaginary portion, so there is no real. The real portion is 0, right? So we're here at 0 on the real portion right here, and we just simply go up 5. 1, 2, 3, 4, 5. So that would be point 4. Point 5 is a negative 8 in the real portion. So we would be at 1, 2, 3, 4, 5, 6, 7, 8 right here. That's point number 5. And lastly, point number 6 does not have a real portion, so it's going to be on the imaginary axis at a negative 3i, 1, 2, 3. That would be point number 6. Okay, let's go on. That's pretty easy. Let's go on to the next little piece that's be in your book, and it's called the equality of two complex numbers. And basically all that is that it says if two complex numbers are equal, then their real portions must be equal, and their imaginary portions must be equal. Say, for example, on this one, we see that this complex number, 2x plus 7i, is equal to 10 plus yi, so that the real portions must be equal to each other. So 2x must be equal to 10, x would have to be equal to 2. And then the imaginary portions have to be equal to each other. So a negative 7i has to be equal to yi. We could divide both sides by I. And we get a negative 7 is equal to y. So this problem said find the values of x and y that make this true. And I found those by simply just setting the real and imaginary portions equal to each other. Correcting the first one, dividing by 2 gives me x equal to 5. Yeah, that's better. So let's work a couple problems with this. So what we see is it says find the values of x and y that make the equation true. So what we know is this is the real portions here. So that's pretty easy. X must be equal to 9. And then for the imaginary portion, we know that 3i must be equal to a negative yi. So, we really don't even need to divide both sides by I. You could see that 3 would be equal to a negative y, so a negative 3 would be equal to a positive y. So if you wanted to write a little equation, you could do it. On the other one, we have 9 would be equal to a negative 2x, so 9 is equal to a negative 2x. So a negative 9 halves would be equal to x. On the imaginary portion, I get 4y is equal to 3i. So the 4y must be equal to 3. Y must be equal to 3/4. Okay, the next piece is adding and subtracting complex numbers, and this is actually a lot easier than it sounds. When you add or subtract complex numbers, you treat the I just like a variable x. They simply add and subtract just like variables. So anytime you get an I squared or something like that, you're going to have to change the I squared to a negative 1. But other than that, everything is the same. So what this would be, let's take a look at the first problem. If I want to rearrange this, I would have 8 plus the 5. Then I have a minus I plus 4i. And this is just going to add like x's. So 8 plus 5, that would be equal to 13. A negative I plus 4i would simply be plus 3i. So I treated that part just like I would any variable. Let's look at the next one. I have a 7 minus 6i. Now then I distribute my negative into the 3. That would be minus 3. And I distribute the negative into the negative 6i. So a negative and a negative would be plus 6i. Okay, now I can rearrange those to look a little better. If you want me to, like that. And now what we can see is we have 7 minus 3. The real portions would be 4. And for the imaginary portion, I have a negative 6i plus 6i. That's going to be 0. So the imaginary portions go to 0. Okay, let's do this last one. I have 13. Now I'm going to distribute the negative in, minus 2. I have a negative distributing to the 7i, so that's minus 7i plus 5i. So the real portions here would be 13 minus 2. That's going to be equal to 11. And then I have a negative 7i plus 5i would be minus 2i. Okay? Let me move on now to multiplication. That sounds difficult, but it is not. We're going to treat this just like x's, except, here's the big thing now, if we have an I squared, we're simply going to change that to a negative 1. So let's go ahead and multiply this first one. The 4i multiplies in to the negative 6, giving me a negative 24i. Now the 4i multiplies by that I, giving me a plus 4i squared. Well, this I squared is really equal to a negative 1. So I can rewrite this as a negative 24i plus 4 times a negative 1. Now I know you guys are not going to I know you guys are not going to be, maybe skipping a step there or whatever. You can just see what's going to happen. That's going to be a negative 4. So I've got a negative 24I minus 4. Now what we want to do is we want to write this in the standard A plus BI form. So we'll always put the real number first. So that would be a negative 4 minus 24I. That's how we would arrange that. Okay? So let's go on to the next one. Here I'm going to use the distributive property of the FOIL method. So the 9 multiplies by the negative 4. That's a negative 36. The 9 multiplies by the 7I. That would be plus 63I. That would be plus 8I. And then lastly, I have a negative 2I times 7I would be a minus 14I squared. Well, a negative 14I squared, this I squared part right here, is simply going to make this 14 be a negative of a negative. That would change that to a positive 14. So let's rewrite it. A negative 36 plus 63I plus 8I. And now my i's will combine and my real number portions will combine. So a negative 36 plus 14, that's going to be a negative 22. And I have 63 plus 8 would be plus 71I. Okay? Looking at the last one. Now this is a difference of squares. Notice this. 3 minus 2I, 3 plus 2I. That was a difference of squares that we factored. Let's see what happens here. This is going to be kind of neat. 3 times 3, okay, that's 9. 3 times a plus 2, plus 6I. A negative 2 times 3 is minus 6I. And lastly, I have a negative 2I times 2I. That would be a minus 4I squared. Well, look what happens to all my I values in the center. They're simply got a plus 6I minus 6I. They're going to go away. So I have 9 minus 4I squared. But I squared is a negative 1. So this really becomes 9 plus 4 is equal to 13. So when I multiplied a complex number that sets up as a difference of squares, the imaginary part goes away and I'm left with the real number. This is called where you have 3 plus 2I, 3 minus 2I, where the numbers are the same, one's a plus, one's a minus. These are called complex conjugates of each other. And anytime you multiply a complex number by its complex conjugate, you get a real number at the end. Okay, so I think that's it. So we're done.